Hi, we're Assistive Technology for the Visually Impaired with Bridge2Africa. Our team is consisted of me, the team lead, Nadia Jafar, Robert Lattis, Adrian Inocencio, Abby Bizane, and Sean Mien. We have a variety of different expertises in technical and non-technical fields.
This is Junior. Junior is a student like any other. He likes to play with his friends at recess and listen to music. However, there's one thing that distinguishes Junior from his peers, and that is that he is visually impaired. For this reason, he's having trouble in class and he's falling behind. This is because his classroom is sight-based and he can't follow along with his peers. For this reason, we've paired with the Siboneyele School for the Visually Impaired located in South Africa. Their mission statement is to use the internet as an educational tool to help these visually impaired students bridge the gap in the shortcomings of the average classroom.
Our primary stakeholder is Bridge2Africa. They're a nonprofit organization established in 2013 based in Johannesburg, South Africa, and their purpose is to enhance communities through technology and education. They've done this in the past using mobile computer labs that they've bused around to schools around Johannesburg to teach students about digital citizenship. Their director, who is our main point of contact, is Justice Gumbo Chuma, who we talk to on a weekly or bi-weekly basis. The secondary stakeholders include the Siboneyele School for the Visually Impaired, the school in Johannesburg, who we are partnering with in order to develop our solution for, as well as students who are blind who are directly interacting with the technology, the families of those students who are dealing with the emotional or financial strain, as well as Daredevils, who is an on-campus advocacy group who we are partnering with to test our solutions. There's several challenges being faced by students who are visually impaired, especially when it comes to navigating the internet. We've broken those down into 4 main categories. First one is cursor-centric websites, in which students have a difficult time navigating a web page when most of the navigation is done using cursor manipulation. Then there's stimuli overload. This occurs when it is very difficult for a screen reader to parse through a website because there's many different links, hyperlinks, things like that that the computer can interact with. Then there's image-heavy information, so web pages with a lot of images are very difficult to access for students who are visually impaired, as well as online verification.
So the criteria for our project is that it needs to be first low cost. A lot of the current Braille displays out in the market right now are really expensive, and one of our main goals is that we want to make our project accessible to the public. Another criteria is that it needs to be user adaptable. Our design and our project aims to be part of the education market. We want to market towards there. For that, it needs to be user adaptable because our project is going to be used among many different age groups and different grades. And since again this is being towards the educational market, it needs both intuitive and engaging because this is going to be used for children and people out there. They need to be able to use their device to learn and be able to use the benefits of a Braille display.
There are current solutions that exist out there, which include screen readers and Braille displays. Screen readers, like JAWS, NVDA, VoiceOver, aren't super compatible with every website, and they're not entirely a solution for helping students learn information because audio cues leave students very passive. They're not interacting with the material. It doesn't activate the kinesthetic part of learning, and so it leaves students passive and they don't retain the information. Braille displays, on the other hand, do activate this kind of part of learning, but they're really expensive, they're not incredibly intuitive, and they're not specifically designed for education.
So just to give you some insight in how Braille works, it's a transcription of an already existing language, and we're using the Unified English Braille Code as part of our product. However, it could be compatible with other languages. And the reason why we like to emphasize this is because Braille literacy rates lead to a higher employment rate, which is a problem that these children who are not retaining it in their classroom face. This is an overview of how our solution would look. So as you can see here, there's a hardware component which would connect to a user's personal computer via a standard USB cable. And then on the software side, they would download our Bridge2Africa software on their personal computer, and they would be able to traverse through the internet and have it print textual information in Braille that would display on the hardware so they could interact with it. So to give you some more insight, we have a user scenario in which a student, the user, is trying to navigate to the ASU homepage. So they would begin by connecting our hardware device to their personal computer. Once their device is on, they would launch the Bridge2Africa software, and once inside the application, they would open a internet window. So this is, in the situation, a Google Chrome browser, and it's the standard Google Chrome browser. So once they've opened this, they use their keyboard inputs and type in ASU. Once they've typed this in, they press enter, as is the convention, and now the Google Chrome browser is searching. And on the back end, that information gets sent to our application, and our software basically has an algorithm that traverses through all of these search links on the first page, and it looks at the HTML markup and decides how accessible it would be for this student to use based on the amount of images in each website, based on the amount of subscripts and superscripts and things that make it harder, easier for the student to read with our hardware. So once it has determined if a website is hard or easy to use with the device, it will label each website alongside the title. So here you can see that it says high difficulty and low difficulty. Now the user is prompted to this article title, and they'll read it in hardware on the Braille display, and they'll see Arizona State University, learn online with ASU, as it says right here. They decide that they don't want that, so they press tab, and the software will then print the next article title. So now they've come to Arizona State University, which is the home page, and then they press enter because that's the website they were looking for, and they're in the web page.
So for our hardware prototype, here's what we've currently implemented. So this is how, in the future, our hardware solution will look like, and this is what we've been able to actually implement into our current existing prototype. So the point of communication between the computer and our hardware is through an Arduino Uno. That Arduino Uno is communicating with two different ICs, a shift register and a decoder. Now this decoder is essentially picking character by character which Braille character should be activated, and the shift register is picking which pins within that character should be activated. So basically these two work together in tandem, synchronously, and right here you can see a 5-character grid. We have actually implemented a 10-character grid of this. Now there's two different directions for hardware. One of the directions for the actual pin mechanism is using micro actuators. That is essentially meaning that we are building really tiny linear actuators that are size of the Braille pins we want to use. There are several different technologies for this that we are currently looking into. And another direction is what we call clever layout, and that's essentially arranging stepper motors, which is existing technology adjacent or perpendicular to the linear motion. Basically, what the pros and cons of these are is a micro actuator approach would be requiring us to invent a new mechanism, building it from scratch. The clever layout approach, we can use existing technologies, but it will be more expensive down the road in terms of cost and equipment. Now, here's kind of what approach 1 looks like. Approach 1, again, is micro actuators. So what you see down each one of these are linear actuators the size of the Braille pins that we desire. So we've kind of created a rough estimate, and we are predicting 2.8 milliamps for each coil. This is really preliminary, but if we were to construct solenoids in order to push or drive our mechanism, that's approximately how much how much energy it would take. So the second approach is what we like to call clever layout. Rather than using linear actuators, we're going to actually use motors and harnessing the rotational motion in order to push these pins up. So this would require the motors to not actually have to be directly underneath each pin, so that this would save on space, but this would be very difficult to implement into a larger scale solution.
So as we discussed the different hardware features and our current implementation of the hardware, we're now going to go on to the software. How does this all connect together? Well, with our software decomposition, a user is going to first open our Bridge2Africa executable. The program is then going to start running. On the program itself, we're going to have different options where they can, if they click on the settings button, they can program their own different shortcuts and then modify kind of the voiceover that goes on within the program. What I mean by programmable shortcuts is that when a user, let's say, press Alt-V or Alt-O, a particular function of our software is going to do something. In our case, let's say a user presses Alt-O, it's going to open a web browser for them. When they do, when they do the O and a web browser opens, they can do different. The program's going to be listening to that particular web browser, and they can use the web browser for normal internet functionality. When they're doing the normal internet functionality, they can do two different type of shortcuts. One where they can kind of read a different accessibility hyperlinks on the website and be able to judge what type of how difficult that website is, as we discussed before with this accessibility rating. The other shortcut is to actually start parsing the information on the website and be able to translate that to Braille, and then be able to go through the microprocessor, our hardware side, and actually have pins that come up. So our software has four main features. It gets information from the website and translates all that information to Braille / to speech. Another thing it does is that it's able to traverse the different hyperlinks on a website and again give the user a kind of a summary of what's on that website they're going to go into, and kind of the rating, how difficult is it for them to traverse or navigate through that next website they're about to go through. Another thing is that what our software does is really simplify the website navigation and the Braille translation of the website they're going into. And another thing that we want to feature is kind of more of an educational feature where they can be able to use the speech, the voiceover, and Braille, and be able to read Braille and synchronize them together so that the user can not only listen to what is being said, but also be able to read it on the Braille display. Another thing that we want to focus on is that we're not trying to replace screen readers, but we're just trying to supplement them. We want to make a ready, good solution even better.
So this is the current model of the prototype that we have printed using a 3D printer. And in this file, you can see that there's multiple sections. This section is just for the electronic components, like the breadboard and wires to sit. Here we have a compartment where the solenoids, which are the pins that push up and down based on an electric impulse, this is where they sit. And what we're currently using for our prototype is pens, and so the pens are threaded through here, and the tip of the pen sits here at rest, and then when it's told by the solenoid to push up, it pushes up through this barrier and displays at the top, depending on which character we want to display.
So what we have in these two images is what our working prototype is in terms of our signal data path. So what we have here are exactly what the flowchart earlier showed. We have an Arduino here. We have several ICs that are controlling this is the shift bit. We have some switches over here. And then each one of these 6 LEDs represents one character. So we're not using solenoids at the moment. We are using LEDs just to show the path that the data is taking.
So for our cost, we're going to aim towards a total of $300. This kind of includes the different ICs and the circuitry that goes on within the Braille display itself, the PCB assembly, the building our own custom board, the micro pin mechanisms, the thing that actuates going up and stuff, and then the housing and casing itself. For the software side, we totally want to make it open source software, so it's going to be completely free, and there's going to be no cost with that.
So here is just a timeline of our future goals. I know it's kind of hard to read, but basically we're just working on integrating the hardware that Rajat was talking about with the software that Adrian was talking about, and developing a full-scale product. Hopefully by the end of the semester, which will end in May, we'll have a full-scale prototype, and then hopefully by December we'll have a manufactured final product.
Thank you so much for your interest in our project. If you have any questions, feel free to email me, the team lead, at this email here, and we will be able to respond to those promptly. Thank you.